Greetings, everyone, and thank you for participating in today's Trident Academy session entitled AV over IP Design and Best Practices, presented by Rito Shpuri, Senior Sales Engineer Networked AV at Atlona. This is Mahmoud Nashat, Regional Business Development Manager, and I will be moderating the webinar today. The webinar will be starting shortly. If you have any question, please submit them through the Q&A functionality in the control panel. Rito will be answering all your questions live at the end of the session. Now, I will leave the stage to Rito.
Hello, everyone, and good afternoon. My name is Rito Shpuri. I'm the Senior Sales Engineer for Networked AV at Atlona and looking for the EMEA region. Thank you in advance for sharing your time with us today and to participate in this Avrp webinar, where we talk about design and best practices in Avrp network. So I will still wait a minute. I see attendees are still coming in. Okay, now that's fine. So we will start with the first slide. And of course, you will also see my contact details in the last slide. And also we will share this presentation afterwards. So let's start by looking at the agenda of today. So I will talk about how Avrp systems work in pretty global speaking. Then we will look into the different network topologies. We will talk about what is Unicast compared to Multicast, what is the benefits of both of the systems. And then some technical terminology like trunk port definition, Igb carrier. Don't be afraid, it's not going to be a Cisco CCNA course compressed into 1 hour, but it's just that you hear about these terminologies. And of course, also you will get the presentation, so you can always pull the presentation afterwards if you're in designing a project, and you can see what this actually means and what is the effect in an actual configuration. So we will not go into too much detail, so I will not show you today how to configure a network switch, but we will talk about the most important terminologies here, like the multicast routing. You don't need to do this, but in case you have a need in a project, at least your reference to the multicast routing, and you can pull the presentation, see, oh, okay, it's this and this. This is what is recommended. Then we will talk about VLANs and segregation. So what is best practice for what kind of requirements? We will do some quick bandwidth calculation examples, not rocket science, but really basic. So you start to get a gut feeling of what is required and what kind of numbers we are talking. What is a virtual matrix? How does control work? And where does the management take place in an Avrp network, of course? And then again, some acronyms like PoE. You might have heard about this. This is the power over Ethernet. So all our endpoints are powered from the network switch. And then we have a couple others, which we will talk one by one. And then we will close with important design questions. This is mainly to prepare your project. If you're a consultant, you want to have a list of questions that in the first meeting with the customer, you want to get answers to these questions in order to have a proper continuation of the planning of the project, not to miss anything. Good, so then let's dive right into the first slide. This is already an Avrp network, is the most basic one. It's so-called point-to-point. So we have, I will quickly find my laser pointer here. Okay, so here we have any source. In this case, it's a set-top box to provide TV signals to an Avrp network, but it can also be a DVD player, a Blu-ray player, a camera. It can be a laptop or any kind of computer. So we just refer to this as a a source, an AV source. Typically, these sources, they have an HDMI cable. They go into what we call an encoder, because the HDMI signal cannot travel over Ethernet networks. It has to be, first of all, from the connector point of view, the HDMI has to go into an Ethernet standard, but also the data rate will be too intense. To give you a figure, like a 4K signal in the fullest flavors of colors and frame rates will be up to 18 gigabit per second as the data rate. So the 18 gigabit per second will be too much for the network. Of course, if you only have one, that will be easy, but if you have a couple dozen signals, that will be too much. So the encoder takes care of data compression. And of course, we don't want to sacrifice the image. So the Atlona system is using a lossless video compression. And we will talk about different codecs and their positioning later on. But this device does two things. So the HDMI connector is translated into an RJ45 that is compatible with Ethernet protocol that can go over a network, and also it reduces the data rate. So once the video and audio packets are available on the network, we can pull them out at any point where we want by a device that is called a decoder. So first we have an encoder, and then we have a decoder. Again, the output will be an HDMI, and it can go to any device that has an HDMI input. Typically, it's a display or a large screen format display. It can also be a projector. It can be a recording device or anything similar. So to summarize, the basic AV over IP system consists of at least one source and one display and one encoder, one decoder, and of course the network. The network basically provides the interfacing towards the encoders and the decoders. So that was a pretty simple design. Let's go a little bit more complex. This is a whole house video system that we can find in a residence, for instance, or that we can find in a sports bar or anything light commercial. So they typically have different zones. For instance, here we have a media closet that contains all the sources. So they have set-top boxes, they have media players, Apple TVs, Blu-ray player, or even PCs. All of those sources, they have their encoder. In Atlona, we have single channel encoders, but we also have dual channel encoders. So then you could use two set-top boxes and just use one dual channel encoder. That sends the video stream to the network, and from there it can go into the home theater, it can go into the media room, bedroom, if you have more than one bedroom, if you have a kitchen, a pool area, and so on. So this is a multi-zone system, but still using a single network switch. It's not a corporate network in that case. Corporate networks, they have different switches for different applications in different areas. Here in residential applications or sports bars, light commercial, you typically have one single switch that can be a 24-port switch, that can be a 48-port switch, that can be a stack, but it's typically one switch or a stack of switches in one physical location. Hence, the design of such a system is pretty easy. Another application that we can do with AV over IP is video walls. Here in this example, it's just a small video wall. It's a 2x2 video wall, but the concept is the same. So we have somewhere our sources. You see here the dual channel encoder I mentioned previously. So we have two set-top boxes, two HDMI cables going into one dual channel encoder, and then this device in that case has 2 gigabit port links to the network switch, and from there we have 4 single channel decoder. So each of the 4 displays has its own dedicated decoder. The displays can be landscape orientation, like you see here, or they can also be in portrait rotation. So sometimes for lobbies, we make video walls that are a 3x1 a 5x1 or even a 7x1, because typically lobbies are pretty large but not too high. So we do support image rotation in our OmniStream decoders. So we can take any source. For instance, if it's a regular source, will be a 16:9 landscape. But then if you have a 2x2 landscape, it will still be 16:9 landscape. So you can show this one source across the 2x2 displays. But in case you want to do rotation, you can use a 3x1 vertical displays, and it will be almost like a 16:9. And then you can have the landscape source on that portrait video wall. So what is the purpose of a video wall? Well, multiple sources can be shown simultaneously, either one source per display or one source across multiple displays. And there are a couple of limitations, like the maximum size of the video wall. So we have made pretty big installations, 20, 30 displays in a row around a circular lobby, for instance. You can do that. So the number of video wall is not limited, but what is limited is the number of displays that show the same source. So if you have a special source, very high resolution, you want to show it on a lot of displays, you can do that, but the limitation in this case is 16:16. So of course, 16 multiplied by 16 is a huge number of displays, but a 16:2, this is something we can see in a control room, in a network operation center. But typically these video walls then are segmented. So again, if you break up a physical video wall into segments, this limitation is gone. And then the next one will be a conference room, a meeting room, a boardroom. And I will want to stay a little bit longer on this slide, because this is the kind of application where we see most of our devices going in. We will start with a small setup, and then we will gradually add components to this concept. So again, we have here a single encoder. It has a laptop connected. So in a meeting room, you go into the meeting room with your laptop, you connect it with an HDMI, you send your audio and video via the encoder to the network. So the video signal is being picked up by the decoder and is being shown on the screen. That can be a display, that can be a projector, of course. The audio signal from your laptop can either go directly into the amplifier. So in this case, this is a network enable amplifier that can receive network audio. And of course, then the amplifier has speakers connected. That can be ceiling speakers, that can be front speakers, or a combination of the two. If you want to enhance your audio, you can use an audio processor, the so-called DSP or digital signal processor. So in that case, your audio from the laptop does not go to the amplifier directly, but it goes to the DSP first, for instance, to be mixed with some microphones. In this case, the microphones are directly attached, but again, that can be networked microphones. I will come back to that in a minute. So then the audio processor mixes and levels all the signals. In case of a video conference, it will also take care of the echo cancellation, for instance, and then sends the audio over the network to the amplifier, where again it goes to the speaker. But our systems, they do not just send audio and video. We can also send USB peripherals. So when you want to send USB peripherals over a network, you need an additional device. We call it Omni 311, and basically it is a host adapter. So it has a USB port that goes to the host. In this case, our laptop, our computer here is the USB host. And this can then translate into Ethernet packets, Ethernet protocol, connect to the network. So now where are my peripherals? You can add peripherals like a camera. So if you want to do a video camera, a video conference, you will have a USB camera, but you want to convert it to Ethernet protocol first, so it can connect to the network, And now it can be picked up by this host adapter and can be sent to the PC or laptop. So now if you're in a video conference, you connect your HDMI, but you also connect your USB and you get the peripherals of that room. Peripherals don't stop at the camera only. We can also have a touchscreen. So now you see that we have added this additional USB line because this is an interactive display. So it's a touch display. It can be used for teaching in universities, in schools, but also in collaboration rooms, in enterprise applications where people want to interact with an application. So the application is running on this computer. It can be a simple PowerPoint, but it can also be something much more advanced like a computer-aided design or 3D modeling and so on. So the application is running on your own PC that you bring to the meeting, but you can control it from the interactive display. USB goes here to this peripheral adapter, travels over the network to the host adapter, and ends up at your computer. Additional USB peripherals that you are certainly familiar with is keyboard and mouse. So in case the computer is somewhere hidden away in a sideboard, in a furniture, you don't have access to its built-in keyboard, but then you can just use keyboard and mouse that is available on the meeting room table. You cannot connect it to this peripheral adapter, although there are 4 peripheral ports, but they are in physical separate locations. So here we have a display on the wall with a camera right on top of it. So this peripheral adapter is also somewhere behind the display at the wall, while this adapter is most likely being installed directly into the conference table. So different physical locations, but those adapters can be paired with this host adapter up to 7. So now we have 2, one here, but you can add more. You can have an additional camera in the front, you can have a camera in the back, in the ceiling. So you can add these USB adapters and you can pair up to 7 to one host adapter. This is controlled via the API. The API is the application programming interface, which again can be controlled from a touchscreen. So this small display here is a velocity touch panel, a VTP so-called. We have it in 5.5 inch, we have it in 8 inch, in 10 inch, or you can use your own touchscreen. So then this control screen is also connected to the network simply via a PoE line, so it's also powered from the switch, and talks to this control processor. The processor is also network-based, so it can sit anywhere on the network. In this schematic, it's sitting in the same room, but it can also be sitting outside of the room. So for instance, if you switch between 2 computers on this touch panel, then the touch panel sends the command to the controller, and then the controller controls this box, for instance, but also can instruct the decoder to pull a different video stream from the network. Next one is a DSP integration. So we already had this audio processor in the room to take care of the microphones and the speakers, but now we are adding an additional USB connection. So between the audio DSP and this peripheral, there is now a USB connection. So the audio DSP also ends up at the laptop as a simple speakerphone. So no driver installation needed. It will work with PC, with Mac, with any kind of operating system. Simply connect the USB here, and your laptop will see a speakerphone, but it's not a physical speakerphone. It's a very complex audio infrastructure in the room. You have microphones, basically those microphones that can be ceiling microphones or table microphones or front wall microphones, any kind of shape. And also the speaker in that case is a proper amplifier with powerful speakers, not just a simple speakerphone. So concerning the network audio, all the microphones, all the amplifiers, all the speakers can be networked audio devices in either Dante protocol or AES-67 format. once you have this kind of setup, you can imagine it's very easy to extend it. Now we only have one computer in this room using one host adapter and one encoder. But if you add an additional PC, let's say a room PC, fixed install PC that is used for Microsoft Teams rooms, you just add another host adapter and another encoder, and that PC can use the exact same infrastructure, the same peripherals as the laptop. Or if you bring a larger table, you add another connection points because you want to have one connection point in the front and one maybe in the back of the table. So this is very easy to extend. And this is one of the reasons that Avrp is putting so much attention compared to circuit-based like HDBaseT, because HDBaseT works with matrices, with frames. And if that frame is full, but you cannot simply add any more inputs or outputs. Versus with Avrp, you can always extend. Now, I didn't design here the switch. I just refer to this as the Vlan. But of course, that's a set of physical switches. And if you do not have switch ports anymore for the Vlan, you just bring another switch. If you need more bandwidth between two switches, you just pull another fiber. But important takeaway for you is your investment is always protected. So if you build a certain room and then maybe 2 or 3 years down the line, your workflow changes, your work habits changes, you need more displays, you want to add more sources, you will still be able to do that. So just by bringing in new equipment, but still keeping the existing equipment, which is not always the case with HDBaseT. At some point, if the matrix is too small, you have to take it out, you have to bring in a bigger one, and those things are quite expensive. So now let's take it to the next level. We have seen this room and what this room can do, and we call it the all IP meeting space because everything is on the network. And now we grow one step bigger. So we basically take this room, and now this room is here, and we multiply these rooms. So let's say this building has 20 of these rooms alone in this building, but there are more buildings. It's a campus. That can be a university for higher education. That can be an enterprise, a corporate headquarters, for instance, or that can be a palace for some institution. The size is basically not limited, but they have many rooms, and all these rooms, they can send and receive content to each other. So imagine a scenario where you're sitting in a conference and all of a sudden you realize, oh, we are reaching a point where we have to include the finance department, but they are sitting in a different building on the other end of the campus. They cannot just simply come over here. So we just give them a call. They should go in whatever meeting room is available to them in their building. And now you can share your screen to their displays. So they can see what you see, and together you can come to decision quickly. You can collaborate in real time. And this is not just for the video, this is also including audio, and this is also including peripherals. You can send them access to a touchscreen, and they can, from their room, control the application that is running on a computer in front of you. Of course, larger campuses, they have these kind of data centers. So what can we do with a data center? Basically, we can centralize services, like, for instance, control. We have seen before the control processor, which is called Velocity in Atlona world. He was sitting in the room, but it's anyway on the network. So it doesn't matter if it's physically in a room, or it can just be as fine in a data center. We do have small controllers for 3 rooms or 10 rooms or 20 rooms, but we also have the option to deploy a virtual machine that can control hundreds of rooms at the same time. Same goes for the management. All these endpoints, they have to be managed at some point. There is security patches, there is firmware updates. So management can also be centralized. And from Atlona, there is a tool available, which is called the AMS, so the Atlona Management System, which is free of charge and can also be installed in a data center. And from there, it can talk to all the Atlona endpoints and manage them centrally. This is a huge benefit for the department that has to be responsible for the management. Recording and lecture capture. So all the audio and video streams are on the network. So you don't have to bring a recorder into the room, or in case of higher education, like a university, they typically do lecture capture, so they can feed the content into their e-learning system. And if you miss a session, or now with the corona again, the COVID virus, many students, they cannot go to the campus. They have to follow from home. So once all the audio and video is on the network, it's easy to put a lecture capture device just here in the data center. So we have air conditioning, we have power supplies and so on, which is very easy to manage also for the IT. Then audio processing. We have talked about audio DSP, and you can have one audio DSP per room, but it's much more cost effective to have larger frames that can handle multiple rooms. So because the audio is on the network anyway, you can have Dante, you can have AS67, all those protocols, they're on the network. So it doesn't matter if the audio processing power is in the room or is in the data center. But of course, it's much more easy and cost effective if it's combined and relocated at the data center. Then video conferencing. Of course, it doesn't apply if you have a soft codec running on your computer like a Zoom or a Teams. But if you have legacy hard codecs like the older Cisco codecs or Tandbergs, they are physical devices. And typically they used to be in the room. But if you connect them with an OmniStream encoder and decoder, they can also be relocated at the data center. And they could even be flexibly assigned to a room. So for instance, when you have a room booking system, you book a meeting room, but also you book the video conferencing at the same time. And then that piece of hardware is assigned to a certain meeting room for a certain amount of time. And then if the meeting is over, it gets freed up again and somebody else can use it. Even though it's not physically in the room, but you can book it and you can use it. And then there is the digital signage. So that means everything from visitor welcome to corporate content, like a nice corporate video that you want to show in the lobby. It can even include the menu of the day in the cantina and all these different kind of things. So you might want to have here encoders and PCs or signage players and to ingest the content. And from there, you can send it to all the rooms, because in all these rooms, you have the decoders. And then you can even show it not just in the meeting rooms, you can also show it in the lobby, on the video wall, for instance. But you can also show it in the cantina, on the screens where you typically see the menu of the day. And then if you have a famous visitor coming in or an important press conference happening, you can, of course, do announcements, but you can also do live transmission of those kind of events. It's not just for pre-recorded content, it can also support live content. Good, so far for the basics. That brings me to polling question number 1. So you should see the poll number 1 on your screen, and you can just reply. Once everybody has replied, we will see, or basically we will display the summarized results. Okay, so the results just came in. So roughly 1/3 of the participants of today's webinars did not design an Avrp system. And I hope after this 1 hour webinar, you will be much more comfortable approaching designs of Avrp systems. We have seen some setups, some schematics of actual rooms, but let's look at the network requirements. So when we talk about network topologies, we have to start very small and then we go into more complex configuration. So the smallest network topology as such, of course, is a single switch. That's, like I said before, that can be one physical device, but that can be also a couple of physical devices that are stacked. So from most of the switch vendors, you have an option to stack not every model, but some of their models. So basically you put them in the same rack, you interconnect them with a stacking wire, and then you get, instead of one switch with 24 ports, for instance, you get then a stack of 4 switches with a total of 96 ports. So what is the advantage of that? Of course, it's simple. It's easy to manage because you don't have to calculate any kind of bandwidth. Whatever goes into the switch can also go out of the switch. There is no limitation in terms of backplane capacity. Nowadays, almost all the switches you can buy are so-called non-blocking. So the amount of data that goes in is also capable of going out at the same time. But there are limited scalability options in terms of number of ports, but also in terms of where you need those ports. If you have a campus, you cannot work with one single switch because you will need switches on the floors in the buildings, and then you will have more complex structure. For this, because it's easy concept, for this concept with a single switch, Atlona also provides ready-to-use configuration files. On this link, if you click on it, this will show you a PDF document with a list of, I would say it's around 30 to 40 switches that we have tested, that we have validated and certified, but also we are providing a config file directly in the PDF document. So you click on the link, you will download the config file from your web browser, and you can load it to that particular model of switch that you want to buy or that you want to use, and you're ready to go. You have an Avrp configuration on your network switch, you have the multicast enabled, all those things, and you can use it. This is an effort of less than 10 minutes. So then the next bigger concept is the star. So we have one so-called core switch in the center of the star, and then we have the access switches around it. So you see each access switch has one direct link to the core switch. So what is the characteristic of an access switch? Of course, it has PoE because it's connecting to endpoints. The core switch doesn't need PoE because all those switches that are connecting to it, they have their own power supply. So no endpoint should go to a core switch, but they go to access switches that can be Avrp encoders, decoders, that can be security cameras, that can be wireless access points. These are the mostly used endpoints that can also be powered from those access switches. So this topology already allows for more scalability because you can see if you need more ports, you just add an access switch, and as long as you can still plug it in here, as long as you still have available ports, you can just add more access switches. And then, of course, we have to start calculating how much bandwidth we are using here or we are requiring here, and this will be coming up in a minute. This scenario already allows for some limited level of redundancy. So that's already a plus. So for instance, if this switch goes down, then you will still be able to use this switch, and you can still send stuff from here over the core switch to here. But of course, if the core switch goes down, you have to imply different measures for redundancy. Like there is redundant power supplies and so on. But in the star, it's not so easy to make the core switch redundant. This will then be a different topology. So the fat tree adds an additional layer. Before we had the core layer here and the access layer here, and now we're introducing an additional layer, which is the distribution layer. So in real life, that would be the access switch is somewhere on the floor of a building, and all the devices that connect or that are physically present on that floor, they connect to the access switch. The access switch has a connection to the basement, and in the basement there is a distribution switch which connects all the different floors of such a building and will communicate with the core switch, which in return interconnects all the different buildings on the campus. So just that you have an image how this would be rolled out. This fat tree opens much more scalability options. And it also enables highly redundant networks, because now you can also have different core switches or multiple. But on the other hand, it's more complex to manage and it can get expensive. But of course, that's always depending on each project, which one is the best for your requirements. Also, I promised you to explain what is Unicast, what is multicast. Let's start with the easy one, which is a Unicast. So in Unicast, the encoder, which is the sender of the traffic, sends the video packets to the switch it's connected to, and it's typically connected to an access switch. And then the decoder, which is receiving the traffic, has a direct connection here. So the data, when prepared by the encoder, already contains the IP address of the decoder. So the data packets are being sent to the switch, can be an access switch or any other kind of switch. And then the access switch knows, oh, I have in the header of my video packets, I have the information of the destination, and the destination happens to be on the same switch. So I simply forward that traffic to the decoder. So this is the characteristic of Unicast. The traffic, the video traffic or any kind of traffic, always flows directly from encoder to decoder. This is very efficient for one-to-one mapping, but has limited scalability. What do I mean with scalability? If you have one encoder and one decoder, this is a one-to-one. But if you have one encoder and 5 decoders, this is a 1-to-5 mapping. So now 5 decoders want to see the same stream. But I said the data packets, they already contain the destination IP address when they are prepared by the encoder. So that would mean the stream that is going here cannot be used for any other decoder sitting somewhere else on the network. So the encoder would in that case have to prepare 5 times the stream for each individual decoder, which means it doesn't scale. So our encoders, they can send multiple streams, which is a maximum of 4. So they cannot have 5 decoders. That's when we are doing multicast. And multicast is here. So now the encoder is not sending data packets to the decoder, because the encoder actually is even not aware how many or if any decoder wants to see his traffic. Instead, it carries the so-called multicast header. So a multicast is an additional IP address in a specified range. And if this switch receives such a multicast traffic, it does not keep it for himself, but it says, oh, I will look into the network if there is an IGB carrier. The IGB carrier, and I will explain in detail what that is basically the boss of the multicast traffic, and all the multicast traffic by definition first goes to the IGB carrier. So now this encoder sends the multicast out. The encoder doesn't know where the IGB carrier is, but this switch knows. So the switch sees there is multicast traffic coming in. He knows here on this IP address there is an IGB carrier, and he knows he has a connection to that IGB carrier, and he forwards the multicast traffic. Now there is this decoder says, hey, I want to see this video stream, asking that switch, do you have that stream? And that switch says, I don't know, because I'm not the IGB carrier, but I know where the IGB carrier is. And he forwards the request to the IGB carrier, and he says, yes, I have the video traffic. And he's sending then the video traffic to this decoder. So now you see, for this example, one-to-one mapping is not efficient, because before we were sending traffic on the shortest possible way, but now we are consuming bandwidth going to the IGB carrier, going to the core switch. And that's when some IT responsible will say, I don't like multicast because it's not efficient. So yes and no. For this example, it's not efficient, I agree. But if this stream was showing on 500 decoders, it will be very efficient. It's even not possible with a unicast. So in multicast mode, all video traffic will flow to the IGB carrier first. It's very efficient for one-to-many mapping. 1 to 5, 1 to 100, 1 to 500, no problem. One encoder can be shown on hundreds of decoders. Good. Now you heard about the IGB carrier. Let's see what we have here. Trunk ports on a switch are those ports to connect to other switches. So it's not an access port, it's a trunk port. So it goes from one switch to another switch. You will not want to connect an endpoint, a camera, or a Wi-Fi access point to one of those lines. It can either be copper or fiber, doesn't matter. Multiple physical ports can be bonded to create higher bandwidth trunk links. So each manufacturer has a different terminology for this, but typically if you have two links, each of them being 10 gig, and you want to actually send 15 gig of traffic, so 15 gigabit per second, you can create a bond on those trunks, and you will have then one virtual link with 20 gigabits per second, of which you can use 15 or 20 if you like. So how do we compute or calculate trunk bandwidth utilization? We have to consider all multicast sources. So these are our encoders. And they are always sending their payloads, their video and audio packets to the master IGB carrier. It's either the IGB carrier or it's the multicast router. For smaller projects, it's an IGB carrier. If you have really large installation, like I believe the biggest one we did is in Australia for the Deakin University. They had more than 400 endpoints. And of course, this is too much to go to one carrier. So they split up the buildings and the departments into multicast domains where they have their own routers. So if you have another IGB carrier or multicast router, then this will be detected by the access switches, and they will send the traffic to that switch, in brackets IGB carrier multicast router. You can have more than one IGB carrier, but it's always going to be the IGB carrier with the lowest IP address that is automatically selected. This is important to know in the design, but this is also an easy mechanism for redundancy. So if you have your designed IGB carrier and this one fails, then automatically the one with the next higher IP address will be selected as the active IGB carrier. And this is very important. If you're using multicast, all the switches touching the multicast traffic must have IGB snooping enabled. This is basically assuring that the whole mechanism with the IGB carrier works. Multicast routing, I will go quickly over this. This is more for reference. Typically, multicast is not routed from one VLAN to another. So you need to establish a multicast router. It's not a big majority of projects requiring this, but just that you know, it's available. The technology is there, and we call it the PIM, Protocol Independent Multicast Routing, as the most common method. And also within the PIM, we recommend to use sparse mode. So basically, only the multicasts that are requested are also being forwarded. Yeah, that's what I just said. And the multicast router is called a rendezvous point where the multicast traffic first goes, and from there it's routed if even necessary. And this brings me to polling question number 2. So would you recommend A, segregated networks / separate physical switches, or B, separate VLAN for Avrp, or answer C, combine all services in one VLAN? Okay, polling is closed. That's interesting. So the majority of participants recommend to use separate VLAN for Avrp, followed by segregated networks, so separate physical switches. And then, yeah, less than 20% recommends to combine all services in one VLAN. This, of course, there is no right or wrong answer. Everything can work for a certain project, for a certain requirement. If we go to a trade show, we put everything in one VLAN because we know what we're doing and we don't have any other critical services running on the same switch. So we have the audio, the video, the USB, the management, the control, everything is on one VLAN. It's technically possible, although if something goes wrong, everything goes down. That's why the VLAN is the smart thing to do. You can do physical segregation, but it's very expensive because you need to have double hardware, and you lose a lot of features, like if you set up an encoder to do streaming on a certain switch, how then you can control it from a separate physical switch. You still have to connect it to, and it's getting quite complicated. So let's take a look at those applications. This is separate VLAN. So the lower left is the VLAN for OmniStream, so the AV over IP. And then the one in the upper right is the general purpose VLAN or the enterprise VLAN, where you have all your computers, where you have internet access, your emails, and so on. So VLANs create logically separate networks to isolate IP traffic between those VLANs, which is recommended. You can still route control, for instance, from one VLAN to another, but the multicast traffic is automatically blocked and stopped. It will not leave the VLAN unless you set up explicit multicast routing. So it's a safety mechanism. Segregation of networks may also require to run AV over IP on physically separated switches, which, as you can imagine, requires twice the amount of switches, more cables, and it's complicated to set up and complicated to manage. But for sure, takeaway, check your customers' expectations up front. If you're in a high security environment like military and Ministry of Defense, sometimes they actually have physical segregation. So you have to know this in advance. You have to check this with the customer and then basically build the system based on this requirement. So now calculation. First, we go with uplink. So uplink is everything from an encoder to the IGB carrier. I think I have to run a bit quicker on this one because we still have a couple slides before the hour is out. So you see all those encoders. Here's a dual channel model. Here's a single channel rack model. Here is a single channel wall plate encoder. The maximum bandwidth that can be configured is 900 megabits per second for one stream. And this is for visually lossless 4K content. So let's start over here. We have those two sources. Each of them is 900. So that's 1,800 plus the 3,600 coming from those four. And these numbers combined is 5,400 megabits hitting this trunk line to reach the IGB carrier. So you already know, okay, this must be a 10 gigabit fiber or copper link. And then we have two more here in the bottom. 2 times 900 is 1,800. So you already see the dimension of this trunk, but also you notice this switch cannot be a gigabit switch. It must be a 10 gigabit switch. And of course, this is taken into account worst case scenario, so maximum bandwidth. So all encoders will always propagate the reader traffic to the IGB carrier, regardless if any decoders requested the stream. This is important for multicast, and it's important for calculating the uplink bandwidth. As a figure, a reference figure for bandwidth, it's 900 megabits per second for a 4K video source in visually lossless quality. Of course, you can play a little bit with lower bit rates, but it's not recommended. It will only be necessary, or basically reduced bandwidth is not necessary if the network is properly designed and calculated. There is one exception. If you know that you only will do full HD, so you don't have any 4K sources, you don't have any 4K displays, then you can design the system on full HD resolution, which is then half of the bit rate. So 450 megabits per second per each of the source. So then, for instance, if you have a dual encoder here, that's 450, 450, that's 900 on this link. So this could still work on a gigabit port. You don't need a 10 gigabit or 2.5 gigabit port here. But you have to be aware that in the future, the workflow of your customer might change. They might go higher in resolution. They need more bandwidth. And at that point, you might have to pull more fibers to enable more bandwidth. Downlink is just the other way around. So now from the IGB carrier, where all the multicast traffic is available, we go down to all the decoders. So it's the same or almost the same design, but of course the endpoints have changed. So now it's a dual channel decoder that we actually don't sell anymore. Now it's replaced by the single channel decoder. So the same number of ports are used from the switch, but you need just, instead of one device, you will need two devices here. So best practice is always to assume worst case. So that means all the decoders will show a different source. Because the best case scenario, if let's take this switch here and those three decoders, they have 6 outputs. So they are connected to 6 displays or 6 projectors. if there is a situation where all those 6 displays, they have the same source, then on this link, instead of 5,600, we will only have 900 megabits per second. Because the moment that this decoder is showing the video stream and a decoder over here is requesting the same content, the switch is aware that it already has received that packet from the IGB carrier. So it will not request it again because it already has it. And it will just send it this port, it's already sending, and it will continue or start sending the same packets also to the second port for the second decoder, and so for the other ones. If all the decoders are on the same source, you will only see one video stream across your network. But of course, you cannot rely on that. You have to take into account the worst case scenario. And that's also when multicast becomes very effective in the network itself. So the network administrator that previously said, well, multicast is not effective, will now learn and understand that it is in fact more effective than Unicast. For access ports, we recommend always to use 1 gigabit switches. So stay away from 100 megabit because OmniStream will not work with 100 megabit ports. Always use 1 gigabit ports, and also those ports, they should have PoE enabled. I will come back to PoE in a minute. But yeah, we have option to power the endpoints from a power supply, but it has a lot of drawbacks. And then the trunk ports, so all the connections between the switches, they should be 10 gigabit or better, let's say 40 gigabit or even more. Looking at control, this is a snapshot of our AMS. So the Atlona management system, it can show graphically all the encoders here, all the decoders here, and you can just create your cross connections. There is a cross connection for audio, for video, or for both of them, or even for control. So an Avrp system, at the end, it acts like a virtual matrix. It can be controlled from within a room, or it can be controlled centrally. You can control it from a touch panel, from a computer, or even from a mobile phone. You can store presets, and that's very interesting because you, for instance, if you have a town hall meeting every Friday afternoon, you can store this as a preset, and by touch of a button, all your decoders will show the exact same amount or exact same source. But also you can have like emergency situation, fire, evacuation, where you have a special source showing everyone what is the alarm, what needs to be done, if the building has to be evacuated, and so on. Protocols, I will go really quick about this one. Endpoints, important for OmniStream, they are always the regular PoE. So 15.4 watt max, typically it's between 8 and 12 watt. So you don't need the expensive PoE plus or PoE plus plus. We have all those protocols. We have content encryption for security. We have HTTP protection for Blu-rays, for instance. This is required. We have compatibility versus quality of service, of course. And now I'm almost at the end. So these are the important questions that you have to take away. And this is what you have to check with your customers when sitting together and starting design and consultancy on an Avrp. How many sources and display do you have in your system? So, and then following that, where are they? What is the maximum distance between a source and a display? Or to put it around, between a source and the network switch, and then between the display and the network switch, and between those switches. Do you plan on routing any source to any display or having a fixed route? Again, this will be like the presets, because if it's fixed routes only, you can use Unicast, for instance. But if it should be flexible, then I recommend to use multicast. Do you think you will potentially expand this system in the future? this is a tricky one because typically customers are very convinced that what they are designing now will last for a very long time, but nobody is able to see the future. If 2 years down the line, they need to change the system, they need to bring in more encoders, more decoders, it's better to have a flexible structure, which is Avrp. So you can, at any time, you can always extend or add encoders, decoders, or USB peripheral adapters and host adapter. Is the Avrp system required to run on the existing network, or do you plan to upgrade the infrastructure? Did you just upgrade the infrastructure? If yes, what are the characteristics? How much bandwidth is available? Or do you plan to update the infrastructure? And then, of course, you have to carefully look that the existing infrastructure is capable of running the Avrp. What kind of content, like I mentioned, is it the 4K? Is it Full HD? Will it be more PowerPoints? Will it be motion video? This has an impact on the bitrate. Is uptime a concern, or do you have a plan for when the primary infrastructure fails? So in AV, typically customers, they don't think about redundancy, but in IT, of course, everybody does. So we are somewhere in between, or those two are coming together now with the Avrp. So it's important to ask this question, and if the customer doesn't care, well, of course, you can make it cheaper, but still maybe keep a plan B if he wants to have redundancy later on. And I mentioned a couple documents. Here you'll find the link. So we do have an OmniStream white paper that explains the functionality, the bit rates, the protocols. You can download that for free. We have the deployment guide, which talks about network requirements and also IGB carrier settings. If you decide to do your own IGB carrier deployment, then you will find all the useful information in detail in this deployment guide. I mentioned this certified switches document that lists around 30 to 40 switches. It explains the configuration, and with one click you can download the configuration and you will be up and running in a couple of minutes. Professional services is something we offer if you need consultancy, either in pre-sales phase or also during commissioning phase. So we can help you wherever needed, where you have not enough resources or you're still building up your knowledge. We can offer the professional services. And of course, there's also a huge training area on our website. We call it the Atlona Academy, where you can self-register, where you can sign up, where you find hundreds of videos and learning courses, including examens and certifications, and also those will provide CTS points. So if you follow the course, you can add CTS points to your resume. And then we are ready to look into the chat if there are questions.
Thank you, Ritu, for the informative session and your valuable time. Before we start the question, I would like to point out that at the end of the webinar, please be noted that after the session, you will be directed as well as to the landing page that will give you more information about Atlona OmniStream AV over IP. A survey will pop up on your screen to collect your feedback on today's session. Your input is highly appreciated as we are always looking to optimize our work to fit your expectations. Now back to you, Ritu. We have a few questions.
Yeah, I will go with the first one. What is the audio network protocol you're using? So from the encoders, we are sending AES67, which is related to Dante. It's sharing most of the protocols, but it's not one by one. So, but it's supported by most of the DSPs that also support Dante. And then the amplifier I have shown, the Gain 120, can be equipped with a network audio cards which can receive Dante and AES67.
Second one from Sohail Abu Salim. Hi guys. Hope you are doing well. Kindly advise if the single channel OmniStream can support the bandwidth for sending video HDMI along with USB bandwidth for the camera and touch screens.
Thank you for the question. You have seen in the drawing, so the USB is always separated from the audio and video streaming. Because our video stream is so high quality, we need 900 megabits per second, and it has a 1 gigabit port. So that leaves only 100 megabit per second, which would be good enough for keyboard and mouse, but it's certainly not good enough for high bandwidth a camera, for instance. So that's why I decided not to have USB ports on the video endpoints, but to have different endpoints taking care of the USB. So that's the Omni 311 and the Omni 324 that you will find on our website. The good side of doing that is that you have then the full USB bandwidth, so the 480 megabits per second that you can use, but you need to provide a dedicated switch port to those devices.
I have another question about what is meant by AVLAN. Is it separated from the campus LAN and switches?
Yeah, the AVLAN is a terminology that many of our customers are using. It's you don't know for sure what is behind. Is it a physically separated switch, or is it a VLAN dedicated for the AV devices? But in most of the cases, I don't worry too much because it's the AVLAN. I can use it for streaming. If I talk to the network administrator, I tell them, well, on the AVLAN, I have to have these requirements like multicast, IGB carrier, IGB snooping, and so on, and he will set it up for me. And if it's a separate switch, or if it's just a VLAN on an existing network, it's not that much relevant.
Another question about the Unicast. Is it one-to-one communication? Then why same switch is the criteria here? I think he was asking about the Unicast, how to do the Unicast connection.
Yeah, it's true. It's the Unicast and the same switch. It's not related. So you can use Unicast streaming from encoder to decoder on the same switch, or you can use it across the network. So the one is not related to the other.
We have another one in the chat box. Can decoders on a video wall work on a different layout away from having constraint of the signals displayed inside the frame of the screens?
So yes, how we do video walls is we need one decoder per display. That's the starting point. And then that particular decoder can only receive one stream. So that stream can either then be shown full screen on that particular display, or that can do the cropping. So crop and scale. So if you have a 2x2 wall, like in my example, you have the 4 decoders. They will receive with multicast the exact same stream, but each decoder will crop out the section for its display. And then you need a control system like Velocity to manage the decoders, to tell them, now you go to that stream, and now you crop out that area of the screen. And this is how we do video walls. So the big advantage of that is that you do not have a central video wall controller. So again, no central point of failure. And also the video wall can grow later on. So you don't have to specify all the requirements up front.
Another question related to the video wall. Can half of the signal be on a screen and the other half on another screen?
Yes, this is definitely yes answer. So one signal can go across 2 screens, but can also go across 16 screens or 32 screens.
I think Rito, he is asking, or he is referring to one screen can be divided into 2 parts. The first part will have one source, the second part will have another source.
Okay, so the picture-in-picture is not supported with OmniStream.
Okay.
Yeah, for the simple reason that you have one decoder per screen, and if that decoder receives 900 megabits per second, that gigabit port is full. There is no room to receive an additional stream.
Another question related to the Bluetooth connection. Is it possible to multicast signals from Bluetooth remote controller? For example, my client asked me for a solution to multicast game console and be played by anyone in the room having a decoder.
So the multicast game console is not a problem. The game console will have an HDMI output. So the HDMI output goes into an encoder, the Ethernet goes across the network and can be pulled out wherever you like with a decoder to a display. How you manage the virtual matrix is up to the control system. So we have an open API, we have a Telnet API, we have a JSON over WebSocket, we have multiple APIs. You can use the Atlona Velocity as the control system, you can use any other brand as a control system. And then the actual remote controller can be a Bluetooth, why not? It can be your mobile phone, can be a touch panel on the wall, can be a mechanical button, whatever is available.
Another question about what is the AV over IP recommended over HD-based? When is the AV over IP recommended over HD-based?
Correct. That's a very valid point. So as a sweet spot, typically we take 16 by 16. So if your requirement is either having more than 16 inputs or more than 16 outputs, you should definitely look into AV over IP because it might be more cost effective from the start. But also for smaller systems, you have to carefully look. There might be a requirement for expansion in the future. Hence, if you buy an HD-based T, a fixed chassis, and you sell it and you install it and everything is fine, but the customer after 1 year or 2 years want to do more with it, it's not flexible. It can only do what it has been designed up front, versus an Avrp system can always be having additional encoders or additional decoders, or they don't need USB up front, but they want to add USB later on, which we see now with the COVID. Many of the meeting rooms, they didn't have video conference, but now everybody needs video conference. So we just add the USB on top and they will have the camera, they will have the speakerphone, even the DSP or a touchscreen integration.
Another one, I think is the last one, which AV over IP is better, 1G or 10G?
Correct. I did not talk about this one, but of course it's very important to understand what the customer needs to do. If the customer says, yeah, I have iPads and I want to see all my sources on my iPads over Wi-Fi, then he needs something like H.264 or H.265, which is a codec that compresses very aggressively, but results in very low bit rates. So those bit rates you can even send over Wi-Fi. The drawback is that you introduce a lot of latency, can be up to a couple of seconds. So this is absolutely not suitable for any live scenarios. Imagine you are in an auditorium, somebody's on the stage giving a presentation, and the projector or the screen behind the presentation person is an AV or IP source, and there is a huge delay, a lag, then the people in the conference room will be confused a lot because the video is not in sync with reality. So our Avrp system is using 1 gigabit ports, but resulting at a very, very low latency of half a frame. So that's 8 to 9 milliseconds, which is almost not noticeable. And also you don't need to match the video delay with the audio delay, because the audio delay is also a couple milliseconds. And if the video is so fast, you don't have to worry for matching the audio to the video. There are other systems that are using a 10 gigabit ports or encoders, decoders, like the so-called SDVoE alliance. They claim to have like microseconds latency, which is fine, but you will not see the difference between microseconds and 8 milliseconds. But you will see the difference when you calculate the bandwidth, because if you have 20 signals, and each of those signals is 10 gigabit, you talk 200 gigabits per second. And if you go to a university and tell them they have to provide 200 gigabit per second just for the Avrp, they will not accept that kind of project. But if you go with the OmniStream, and ours is 1 gigabit, so that's 20 gigabit, they might have a 40 gigabit backbone, and it might be feasible that the Avrp will fit on top of their existing network.
So finally, thank you, Rito, for your informative presentation. I hope you all enjoyed Rito's presentation and it has expanded your knowledge on the latest trends of AV over IP design and best practices. If you have any question on the presentation, please contact Rito via his email address shown on the slide, or reach out to us at atlona@itrident.com. Please be noted, after this session, you will be directed as well as to the landing page that will give you more information about Atlona OmniStream AV over IP. Once again, thank you for attending today's session. We are looking forward to seeing you in the upcoming Trident Academy sessions. Thank you.
Thank you very much, everyone. Bye-bye.